Hello everyone, welcome to my channel. Today we will learn about the design of compression member. We already studied in our last session the various tension member numericals. So in this session we will learn about the compression member. In this compression member there are two types of numericals will be asked in examination. Especially in the on the strut, and second one is the built up column, or sometime may ask about the channel section will be given or I section will be given. We have to check their capability, load carrying capacity. So today's numerical we will go on through the design of single angle discontinuous strut to carry an factored axial force of 125 kilonewton, unsupported length of member 3.2 meter. Also we have to design its connection by using 20 diameter 4.6 grade bolt. So we are trying to solve this numerical step by step. So in this one our first step is we have to select the section for to carry this factor load 125 kilonewton. So for this in IS 800 2007 clause 7.1.2 has given the area required equal to TD upon FCD, where FCD is the compressive stress. We have to assume initially 80 to 110, we can take in between that one. So we are assuming in this numerical 80 Newton per mm square. So with this calculation the area required we found at this much. So from steel table we have to select an ISA so such that its area is greater than our calculated area. So we are assuming, so from steel table we have to determine the angle equally where preferable, so that its area, sectional area, which is slightly greater than our calculated area. Okay, so I am assuming here I say 90 by 90 by 10. Its sectional area is 1703 mm square. We have to determine its ISA 90 by 90 by 10. It's a radius of gyration value, that is R minimum. It is 17.4 mm. It is also given in that steel table. So our next step is to determine the effective length and slenderness ratio. So in the numerical it is given that the unsupported length is 3.2 meter. We have to convert it into the mm, 3200 mm. We are assuming that its length is equal to 1. L is equal to 32. We are assuming effective length KL equal to 1L, that is the length is given in numerical 3.2 meter. So to determine this slenderness ratio we have to first check in which the buckling class of this section. So from IS 800 table number 2 gives that the classification of section D by T, B by T, B plus D by T. From this we can determine our section is in semi compact or compact or others. So the depth of our angle we have already calculated as 90 by 90 by 10. So in this one and thickness is the 10. Similarly we can determine all these things, and we can see the clearly here 15 it is less than the 15 again. From this condition we can easily identify the section is in semi compact. It is required for our buckling class section, and its class is C. So to determine the effective slenderness ratio we have to determine some following values. So from table number 12, IS 800 2007, class 7.5.1.2. So to determine the effective slenderness ratio and the constant of the slenderness ratio K1, K2, K3, we have to assume number of bolt more than 2 at joint, which is attested to the gusset connecting member as a fixed. So from table number 12, IS 800 2007, clause 7.5.1.2 gives the K1, K2, K3 values. So from this, so the IS code, as we discussed, clause number 7.5.1.2 gives the effective non-dimensional slenderness ratio from this formula, L upon R minimum under root pi square modulus of elasticity divided by 250. For this we are assuming yield stress that is 250 and Young's modulus it is 2 into 10 raised to 5. So with this formula we can calculate the effective slenderness ratio non-dimensional. So for this yield stress ratio epsilon we can determine through this under root of Fy upon 250, and we are assuming the yield stress for the given section it is 250. Likewise we can determine this slenderness ratio also. B1 and B2 we have already selected our section, that is ISA 90 by 90 by 10. So our B1 and B2 it is 90 and 90, thickness is 10. So likewise we can determine easily. After that we have to finally determine the slenderness ratio through this formula by using this constant K1, K2, K3, and we have calculated 1.379. We required this all values for further, and from clause 7.1.2.1 we have to determine theta from this formula 0.5 multiplied by 1 plus alpha, where alpha is the imperfection factor, which is taken from the clause number 7.1.1, page number 35, IS 800 2007. So for our class, that is buckling class C, alpha we can give 0.49. You can see here for buckling class C it is alpha given 0.49, and IS 800, as I told you, this is the formula. So from this formula we calculated theta. From all this value lambda and theta we require to determine the design compressive stress. Design compressive stress, that is FCD. Initially we have assumed it is 80. So actual FCD we can determine from this formula which is given in IS clause 7.1.2.1, page number 34. So now we have to determine this design compressive stress FCD actual through the earlier we have calculated theta and effective slenderness ratio. So from this calculation we have determined this 81.18 MPa FCD. Okay, now so there are two checks for design compressive strength PD and check for slenderness ratio. So check for design, clause number 7.1.1 gives this formula, and here we have to take the area of selected angle section. So after calculation it is clearly shows that the our factor force 125 kilonewton and it is determined 138, which is greater than the given, so it is safe. Similarly for slenderness ratio, table number 3 IS 800 gives that the formula 0.85 L upon R minimum. So through which it is given that clearly the maximum slenderness ratio for single angle section it is 180. So it is we have determined 156, which is less than 180. Hence for slenderness ratio check also it is okay. The last step, design of the connection. It is given in our numerical, it is bolted connection, so we are going to design bolted connection. For bolted connection, we have to determine two cases: design for shear strength of bolt and design for bearing strength of bolt. So in tension member, we have already studied this one. The IS 800 clause 10.3.2 gives this formula for design shear strength of the bolt. Here FUB is the ultimate strength of the bolt, stress of the bolt, it is 400, and the gamma m1 from the table number 5. So likewise we can determine the design strength of the bolt. Next is bearing strength of the bolt. Again the clause 10.3.3 gives this formula. Here KB, we can take a list of this given formulas, that is E upon 3d0, where d0 is the diameter of hole. If our diameter of bolt is 20, then the diameter of hole is it's plus 2, so 22 is our diameter of hole, that is d0. Likewise we can determine these all three values. So list of this value we can get the final value for KB. So after putting all this value in this formula, we'll get the design bearing strength of the bolt. And finally we have to determine the number of bolt for connection. Load upon list of these two values, that is the design strength of bolt and bearing strength of the bolt. So from these two value we can determine the design shear strength of bolt is minimum, that is 45. So we are taking here to calculate the number of bolt, and we have find 2.7, that is nearly equal to the 3 numbers of bolt. So provide 3 number of bolt of 20 mm diameter for given I section, I say 90 by 90 by 10. Okay, thank you. If any query you can write in the comment box.